We walked on the moon and returned alive, but that achievement hides a brutal truth. Doing the same with Mars may be one of the hardest engineering puzzles humanity has ever faced. For many people, the logic seems simple. If astronauts traveled to the moon decades ago, then the red planet should just be the next destination on the same path. Same concept, same physics. Just farther away, right? Not even close. The moon mission and a Mars mission are not simply different in scale. They belong to entirely different categories of difficulty. And the reason for that difference hides inside a single equation. One equation that quietly governs every rocket ever built. And that equation does not negotiate. Let's start with the basics. A rocket works through a simple idea. It throws mass backward and the vehicle moves forward. Newton described it centuries ago with his third law. Push something one direction, the system moves the opposite way. That is the entire principle behind every launch ever performed. Simple to explain. But hidden inside that simplicity is a trap, because the fuel you plan to burn later must be carried from the beginning. Which means the rocket is heavier when it launches. And a heavier rocket requires more fuel to accelerate, which makes the vehicle heavier again. And suddenly you are stuck in a loop where fuel exists mostly to move other fuel. Engineers gave this nightmare a name, the rocket equation. Mathematically, it describes how much velocity a spacecraft can gain. The change in velocity, called delta V, equals the exhaust velocity multiplied by the natural logarithm of the ratio between the vehicle's full mass and its empty mass. If that sounds abstract, the consequences are not. Double the speed you need, and the fuel required does not simply double, it explodes. The curve is exponential. That means every small increase in speed demands dramatically more propellant. Imagine increasing from 3 kilometers per second to 6. Fuel demand doesn't double, it grows drastically. Push toward 9 kilometers per second, and suddenly the rocket becomes almost entirely propellant by mass. About 95%. That is why engineers often talk about the tyranny of this equation. Rockets don't fight gravity, they fight mathematics. Let me give you an image. Picture driving across an enormous desert where no fuel stations exist. You must bring every drop of gasoline with you. But gasoline has weight, so the more you carry, the more fuel you burn simply moving the fuel itself. Add more containers, and eventually most of the fuel is spent transporting other fuel. That is the strange economy rockets live in. Now consider the giant machine that carried astronauts to the moon, the Saturn V. At launch it weighed roughly 6.5 million pounds. And about 85% of that mass was fuel. The spacecraft that actually traveled to lunar orbit and returned to Earth represented less than 1% of the total launch mass. Almost everything else existed just to burn away. Stages dropped off. Tanks emptied. Mass vanished as the rocket climbed. The entire architecture of the vehicle revolved around one idea: shedding weight as quickly as possible. Because the equation demanded it. Now look at what Apollo actually required. To reach low Earth orbit from the surface costs roughly 9.5 kilometers per second of delta V. From orbit to the moon and back adds around 6 more. So the whole journey required about 15 or 16 kilometers per second. Just barely achievable. The Saturn V sat right on the edge of what physics allowed. And it worked because the moon helped. Its gravity is weak. Its surface has no atmosphere. The lunar lander could be extremely light. Half of it stayed behind on the surface when astronauts departed. Every design decision cut mass wherever possible. That is how the mission succeeded. But Mars changes everything. First, distance. The moon sits only a few days away. If something breaks, astronauts can improvise and come home. History proved that. Mars is a different story entirely. At its closest alignment, it still lies roughly 55 million kilometers away. You launch at the correct moment, follow a precise orbital path, and arrive roughly 8 or 9 months later. That is 8 months traveling through empty space. No turning around, no quick rescue, no safe harbor between worlds. If something fails, the crew must repair it themselves or accept the consequences. And every day the nearest human beings grow farther away. Now let's examine the velocity budget. Leaving Earth orbit for Mars requires about 3.6 kilometers per second. Upon arrival, the spacecraft must slow down enough to enter Martian orbit. That costs another 1 or 2 kilometers per second. Then comes the landing. And Mars reveals its first real danger. The planet does have an atmosphere. But it is incredibly thin. Only around 1% as dense as Earth's. Standing on Mars is similar to standing 35 kilometers above Earth's surface. That strange atmosphere creates a paradox. It is thick enough to generate intense heat during entry, so you need a heat shield, but far too thin to slow a large spacecraft safely. Parachutes help, but only a little. They might reduce speed to something like 200 meters per second, which is still catastrophic. So after heat shield and parachute, rockets must fire to perform the final braking. For small robotic probes, that is manageable. For a human mission delivering 20 to 40 tons, it becomes terrifying, because parachutes cannot simply scale up forever. To slow a massive spacecraft, you would need parachutes hundreds of meters wide. That is unrealistic. So the spacecraft must rely heavily on rockets for landing, and every kilogram of propellant used during landing had to be carried from Earth. Think about that multiplier. NASA estimates that delivering a single metric ton to the Martian surface may require roughly 20 tons waiting in low Earth orbit. 20 to 1, just to land. Let that sink in. Now imagine we somehow solve all of this. Assume heroic engineering. Assume perfect launches. Assume astronauts successfully land on Mars. Eventually they want to go home. And this is where the problem becomes truly vicious. Because leaving Mars may be harder than reaching it. Not because gravity is stronger. Mars' gravity is actually weaker. About 38% of Earth's. Escape velocity is only about 5 kilometers per second. But remember where the astronauts are. They are standing on a freezing desert planet millions of kilometers away from the nearest industrial facility. And they must launch a rocket from that alien surface. If the return fuel is brought from Earth, it must survive the entire journey, launched from Earth, carried across space, landed safely, stored for more than a year, then used for liftoff. And again the rocket equation begins multiplying everything. Every kilogram of fuel needed for the return journey is a kilogram that had to be transported to Mars first, which required even more fuel earlier. The cascade quickly becomes enormous. Let's sketch the numbers. To depart Mars and head toward Earth requires roughly 6 or 7 kilometers per second of delta V. With efficient engines, the return rocket might need about 80% of its launch mass as fuel. So a 10-ton spacecraft would need about 35 tons of propellant waiting on Mars. 35 tons. On a world where none naturally exists in ready form, and every kilogram of that propellant would have been launched from Earth originally. You can probably see the nightmare building. The hardest part of Mars isn't arriving, it's escaping. Now step back and consider the entire round trip. Total delta V for a Mars mission sits somewhere between 18 and 22 kilometers per second. Only a few kilometers per second more than Apollo required. But because of the rocket equation, those extra kilometers explode the mass requirements. Going from 15 to 20 kilometers per second may multiply launch mass several times. A Mars expedition might require a spacecraft assembled in orbit weighing tens of thousands of tons. Humanity has never constructed anything remotely that massive in space. And orbital mechanics adds another twist. Earth and Mars only align properly for efficient transfers about every 26 months. Miss that window and you wait. If astronauts land on Mars, they cannot simply depart whenever they choose. The optimal plan requires staying roughly 500 days on the surface. So the entire mission lasts around 2.5 to 3 years. That long stay is not optional. It is dictated by the geometry of planetary motion. During those years, astronauts face radiation with little protection. Earth shields life using a magnetic field and a thick atmosphere. Mars provides neither. Cosmic rays, high-energy particles from distant events, can tear through spacecraft walls and living tissue alike. Over multiple years, exposure significantly raises long-term cancer risk. Proper shielding would require meters of heavy material you cannot afford to launch. Life on Mars would also be completely isolated. Supplies from Earth require 9 months to arrive, and they can only be sent when launch windows allow. If equipment fails, the crew must improvise. If someone becomes seriously ill, there is no evacuation. There is only the training of the astronauts, and whatever tools they brought. Imagine 4 or 6 people living inside habitats no larger than shipping containers. Outside lies an endless rust-colored desert. Communication with Earth arrives minutes late. Help is always millions of kilometers away. Psychological stress becomes a real engineering variable. Fatigue affects decisions, relationships strain, performance declines. These are problems technology cannot fully eliminate. Now return again to the fuel issue. That 35 tons of propellant required for the return must somehow be waiting on Mars when the astronauts arrive. Which means it had to be launched from Earth long before they ever left. Transported safely, landed precisely, and stored for more than a year. Trace the mass backward through the rocket equation, and the required launch mass grows enormous. Fuel to carry fuel. Fuel to land fuel. Fuel to launch the fuel that carries the fuel. The chain becomes almost absurd. With today's technology, the numbers push the boundary between extremely difficult and nearly impossible. So scientists proposed a clever alternative. Instead of bringing the return fuel from Earth, make it on Mars. This concept is called in situ resource utilization. Mars' atmosphere consists mostly of carbon dioxide. Break that molecule apart and oxygen appears. If water ice exists underground, as evidence suggests, you can split it into hydrogen and oxygen. Combine hydrogen with carbon dioxide and you can produce methane. Methane and oxygen together form a powerful rocket propellant. On paper, this strategy is brilliant. Ship a small chemical plant to Mars. Let it run for a year. Gradually fill the rocket's tanks using local resources. Suddenly the mass problem shrinks dramatically. But there is a catch. We have never done this before. Not even once at meaningful scale. Laboratory experiments prove the chemistry works. Scaling that chemistry into tens of tons of propellant on another planet is something else entirely. The plant must function autonomously in brutal conditions. Temperatures can drop below -120 degrees Celsius. Fine dust infiltrates machinery. Maintenance crews do not exist. And the system must operate for more than a year without failure, because if the astronauts arrive and the tanks are empty, there is no second chance. No backup ride home. Even solving the fuel problem leaves other challenges untouched. Landing heavy payloads safely, maintaining life support systems for years, managing radiation exposure, handling psychological strain, enduring 9-month voyages, re-entering Earth's atmosphere at extreme velocity. Each problem alone would be a massive engineering project. Together they form a wall of complexity. Compared to that wall, Apollo begins to look surprisingly simple. I am not claiming a Mars return mission is impossible, but it is far harder than most people imagine. It is not solved merely by building a slightly larger rocket. It requires breakthroughs across propulsion, robotics, materials, medicine, and human psychology. It also requires accepting risks that make early aviation seem cautious. And everyone involved must understand one fact. If something goes terribly wrong, rescue is not coming. There will only be the crew, their spacecraft, and the vast silence of space. The Moon tested our ingenuity. Mars will test our endurance. The rocket equation ensures every kilogram matters. Every decision echoes through the entire mission. Either we bring everything we need, or we learn to build it on another world. Both paths stretch the limits of human capability. That is the real challenge of Mars exploration. Reaching the planet is only half the story. The true puzzle is returning from it. And that is where the universe reminds us how difficult leaving Earth truly is. If this video changed how you think about space exploration, tap like and subscribe to Winds of Thought for more deep ideas behind the universe.